of various synthetic polymers in the textile industry and their advancement. I am Dr. Ashim Kumar Raichaudhuri, retired professor and HOD Textile, Government College of Engineering and Textile Technology, Srirampur, West Bengal, India, 712201. Email akrc2008@yahoo.in. The paper was presented as invited speaker in the International Conference on Polymer Composites, Nanocomposites and Biocomposites 2023 ICPCNB 2022 on December 11, 12 and 13, 2023, organized by Sadbayev University in Almaty, Republic Kazakhstan, in collaboration with International and Inter-University Center for Nanoscience and Nanotechnology, MG University, Kottayam, Kerala, India. The paper was also presented online at the International Conference on Recent Trend in Material Science and Devices 2023 ICRTMD 2023 on 29 to 31st December 2023. Clothing and textile. Clothing and textiles are important in human history. They reflect the material available to a civilization as well as the technologies human has mastered through ages. The human being may have been beginning wearing clothing as far back as 0.1 to 0.5 million years ago. Anthropologists believe that animal skins and vegetation were adapted into covering as protection from cold, heat and rain, especially as humans migrated to new climates. The first figure shows people wearing animal skin or vegetables. Then people started learning making of fabric. The first stage is yarn making, that is spinning. Second is cloth making, that is weaving. Third is dyeing, that is coloration of the yarn or fabric. And finally printing for further decoration. Garments and clothing through ages were developed in different countries according to technologies known, religions and customs. Various types of garments in the primitive ages are shown in the figures. Classification of textile materials. Apparel textile, this includes fabric used for making fashionwear, household textile, which include table linen, bed sheet, toweling, etc. Industrial textile, they are used for making filter, medical textile, geotextile, etc. Medical textile, these are textiles in the medical field, including surgical gowns, wound dressings and implantable devices. Consumer textile, they include fabric for making sleeping bags, etc. Floor covering include rugs, carpets, etc. Furnishing or home textile, these include textile that are used for home furnishing, curtains, upholstery, wall covering, etc. Textile reinforced composite consists of a textile material as the reinforcement phase and usually a polymer for the matrix phase. Manufacture of textile materials. The textile fiber should have high to moderate flexibility, good extensibility 5 to 50%, high fineness, high ratio of length to thickness, sufficient strength to resist breakage during manufacture and use, enough thermal and chemical stability. Now textile fiber may be staple, that is short length, or filament, continuous length. Before invent of synthetic fiber, natural fibers were used, mostly number one cotton and other cellulose from cultivated plants, wool from body of the sheep and silk from silkworm. Those are shown in figure 1 to 3. Natural fibers. Cellulosic fibers Cotton, oldest and most popular for apparel and garment. Hygienic fiber possess very useful aesthetic properties, but cotton plants require huge quantities of insecticides and pesticides. There is non-eco-friendly life cycle. Supply is declining day by day due to land shortage and becoming costlier. Flax, jute and remi are produced from respective plants. Flax was widely used for king and emperor's durable dresses. Jute and remis are used for non-apparel textile. Proteinous fiber, wool obtained from seahairs and is used for warm clothing. Other hair fibers are alpaca, mohair, Kashmiri camel, etc. Silk is obtained from silkworm and used for delicate textile fiber. Both wool and silk are quite costly. Regenerated and synthetic fibers. Regenerated fiber, several natural non-fibrous cellulosic like bamboo and non-fibrous protein materials like casein can be chemically converted into fibrous form. For example, artificial silk cellulosic and casein fiber proteinous. They are cheaper but performances are poorer. First artificial silk was developed as early as in 1894. Synthetic fiber. These are man-made fiber synthesized chemically from simple chemicals of low molecular weights, mostly petroleum byproduct. Synthetic fibers are numerous. Polyester 1953, polyamide nylon 66 1935, polyacrylic acrylic or modacrylic 1949-1950, Aramids 1961, polyalkene polythene 1898, polypropylene 1954 and polyurethane spandex 1959 are used in textile industries. The number shows under bracket are the years of introduction. Synthetic fibers. The three most important synthetic fibers are polyester 55%, nylon 5% and acrylic 20%. The percentages are of total global fiber production. Many other synthetic polymers are also spun into fiber to lesser extent. The advantage of the synthetic fibers are high modulus and strength, reasonable stiffness, stretchability, wrinkle and abrasion resistance, relatively low cost, convenient processability, tailorable performances, easy recycling. The disadvantages are hydrophobicity, less wearing comfort, low dyeability, build-up of electrostatic charge, tendency to peeling, difficulties in spinning, insufficient washability associated with hydrophobicity. Hence, various physical and chemical methods are used to improve the properties of synthetic fiber. Polyester fibers. Polyethylene terephthalate or PET. A linear polymer consists of at least 85% by weight of an ester of a dihydrate alcohol such as diethylene glycol and terephthalic acid. Great versatilities of PET: heat state stability, high strength, high modulus, low shrinkage, good light fastness, high chemical and environmental resistances. Most of the fiber are spun by melt spinning method. Stages are melting of polymer, spinning and then drawing or stretching. First figure shows polyester chip, second figure shows adding of anti-static, fire resistance, etc. and then pass through spinneret. The hole may be circular, trilobal or pentalobal, etc. Then after passing through spinneret, it is drawn or stretched or elongated up to 5 times to its original length to align in a parallel formation. Drawn fibers may be textured or twisted to create softer or duller fabric. Typical polyester has 50% crystallinity. Chemical reactions during polyester manufacture. First stage, terephthalic acid is reacted with methyl alcohol to form dimethyl terephthalate. Then dimethyl terephthalate is reacted with ethylene glycol and we get diethylene glycol terephthalate. That is polyethylene, that is polymerized to get polyethylene terephthalate. When blended with cotton, polyester improves shrinkage durability and wrinkling profile of cotton. Main drawbacks of polyester are low moisture regain, 0.4%, accumulation of static elasticity, high soil pickup during wear, difficulty to remove during washing, formation of pins or bunch of fibre on the fabric surface, and polyester is a flammable fiber. Modified polyester fiber. First, low peel polyester PET, LPPET. Peel is a small ball of fiber that form on the piece of polyester cloth. It is an undesirable surface defect of textile caused while washing and wearing of the fabric. Polyester fiber has peeling tendency which can be minimized by reducing the abrasion resistance so that fiber breaks off before the formation of large peels. Low peel PET can be obtained by incorporating terephthalate of barium, calcium or zinc or organic compounds of antimony, iron or chromium in the polymerizing mass. Hydrophilic polyester. Additives like 5 to 10% by weight of sodium sulfate, particle size less than 3 micron, as slurry in glycol during polymerization. Addition of a water soluble aliphatic polyamide may result polyester having moisture absorption of at least 1% at moisture absorption of at least 1% at 65% relative humidity and 21 degrees centigrade and a water retention capacity of at least 15%. The soil resistance property can be enhanced by adding polyethylene glycol or tetraethylene ammonium perfluorooctane sulfonate to the polyester melt. Improvement of dyeability of polyester fiber. Carrier-free dyeable polyester CFDP. Physical method by making number one by making certain change in melt spinning, drawing and heat setting operations. Number two, air texturizing and filament mixing. Third, the most important technique is the draw texturizing of partially oriented yarn. Chemical method using melt additives like polyethylene glycol, that is PEG, additive acid and azillic acid. They form block copolymer lowering TG about 10 degree and can be dyed deep sets at boil in the absence of carrier. Incorporating modifying agent like polyethylene glycol during trans-esterification, polycondensation or during melt blending. Problem of CFDP are poor leveling or uneven dyeing, lower wash and light fastness of the dyes. Basic dyeable polyester CD polyester PET. Copolymerization with sodium salt of 5-sulfo-isophthalic acid make polyester dyeable with bright basic or cationic dyes. CD polyester has excessively low melting point and fiber spinning is difficult. Polyester. 4 types of spinnerets are used for producing hollow fiber. Plug-in orifice spinneret, a solid pin supported in the center of a circular orifice. It is necessary to incorporate a gas forming additive in the polymer melt. The gas fills the core of the fiber and prevents collapse until fiber solidifies. Tube in orifice spinneret, a hollow needle or tube supported in the center of the orifice. An inert gas or liquid is injected through the needles to maintain the tubular shape until the fiber solidifies or coagulates. Segment and spinnerets with a C-shaped orifice. Polymer solution or melt welds into a tube after extrusion through the seed-shaped die. The gas required to keep fibers hollow. Special spinning. Drawn polyester filaments are hydrofixed in water in the presence of specified surface active agent. Very quick and a more stable pore structure is obtained. The moisture uptake is increased and water retention capacity is higher. The hydrophilic properties is retained even with repeated wearing and washing. A salt forming compound is added for the manufacture of flame retardant and hydrophilic polyester fibers. Surface treatment with plasma. Plasma surface treatment uses a low temperature plasma to modify the surface of a material. Plasma is an ionized gas that contains charged particles that can react with the material's surface. It can be performed in a vacuum chamber or in an atmospheric pressure. Plasma processes are presented on various textiles for cleaning or etching, activation with an inert gas or a non-carbon containing gas such as oxygen, nitrogen, air, ammonia, nitrous oxide or halogen to improve adhesion strength between substrate and adhesive, and plasma polymerization or grafting of various monomers. The effects of plasma treatment: change of properties, reflection property changes, surface hardness changes, it becomes dark repellent, wettability improves, flammability better, adhesive bonding, electromagnetic radiation properties changes, printability improves, hydrophilic hydrophobic tendency changes, anti-static properties changes. The first figure shows three stages of plasma treatment: first activation, second grafting, third etching. The other figure shows plasma reactors. First one is wave treatment of fiber wave, and secondary treatment of individual fiber. Nylon or polyamide. Nylon was first commercially thermoplastic polymer produced by DuPont in 1935. Nylon is a family of synthetic polymer with amide backbones, usually linking aliphatic or semi-aromatic groups. Aliphatic nylon and aramid fibers have less than and more than 85% of the amide group respectively. Nylon 6 production. E-aminocaproic acid form a ring compound caprolactam. By ring opening polymerization we get nylon 6, CH2 5 CONH2 CONH n number, and nylon 6 production. Hexamethylene diamine reacts with adipic acid and we get nylon 6,6, that is CH2 5 CONH CH2NH to the power n. In nylon 6, amide group are located in a continuous head-to-head arrangement, whereas in nylon 6,6, amide group reverse direction, each time in a head-to-tail arrangement. Nylon or polyamides. Nylon 6 is produced by ring opening chain growth polymerization of caprolactam in the presence of water vapor and acid catalyst. It is then melt spun at 250 to 260 degrees centigrade. Nylon 6,6 is prepared by step growth polymerization of hexamethylene diamine and adipic acid and melt spun at 280 to 290 degree. Degree of polymerization of nylon 6 and nylon 66 varies from 100 to 250 units. Properties of nylon. Nylons are strong and stiff fibers. They have recovery property from stage deformation is very good. Excellent resiliency and recovery from bending. Low density, moderately hydrophilic with moisture again of 4 to 5%. Soluble in hydrogen bond breaking solvent such as phenol, formic acid and benzyl alcohol. They have very high abrasion resistance and hence used in rope manufacturing and similar applications which are regularly subjected to friction. Nylons are fairly resistant to chemical attack. They are attacked by acid, base, reducing agent and oxidizing agent only under extreme conditions. Nylon or polyamides may be of nylon 6 or nylon 66. It can be either staple fiber or filament. Staple fiber may be coarser fiber 3 to 120 dtex and finer fiber 0.8 to 3 dtex. Dtex is the fiber weight per yarn thickness, weight in grams per 10,000 meters. Now both coarser yarn and finer yarn are used for making yarns or ornaments. Other than filament yarns are used for conventional articles or spunlace fabric 0.5 to 20 dtex. Major specialty nylons include Quena, nylon 4, nylon 11, nylon 610 and bi-constituent nylon polyester. Nylon is a synthetic polymer that have many uses. Some important uses are fabric and fiber for clothing such as shirt, swimming wear, lingerie, underwear and sportswear. Industrial applications such as conveyors and seat belts, airbags, parachutes, nets and ropes, tarpaulins and tents. Musical instruments such as strings and whistles, artificial fibers and fish nets, plastic for machine parts, sheet, film, pipes and screws. Figure shows different nylon stretchable garments and rope. Aromatic nylons or aramids. Aramid or aromatic polyamide fibers are formed by polymerization of aromatic diacid chloride with aromatic diamines in a polar aprotic solvent such as N,N-dimethyl formamide. The meta and para substituted benzyl dicarboxylic acid chlorides are used for Nomex and Kevlar aramid fibers respectively to react with diamine. Figure shows unit structure of Nomex and Kevlar. Due to linear parastructure, molecular chain in Kevlar are extremely stiff. This crystalline fiber is correspondingly strong and stiff. The aramids are the strongest of the man-made fibers. Fibers are stiff with excellent resilience and recovery from bending deformation. The aramids have very high heat and electrical resistivity, have excellent insulating capabilities and are unaffected by heat up to 250 degrees centigrade. The aramids are extremely resistant to chemical or biological attacks. Aramid fibers are used in fabric applications where high strength and low flammability are desired. Acrylic and modacrylic fiber. Acrylic and modacrylic and other vinyl fibers contain cyanide group as side chains. The fabric containing more than 85% and less than 85% acrylonitrile are known as acrylic and modacrylic fibers respectively. The remaining comonomers are methyl methacrylate, vinyl acetate and vinyl pyridine. Acrylic fibers have found a wide spectrum of use where soft wool-like characteristics are desired, such as sweaters, skirts, dresses, suits, knitted wear, blankets, socks, carpets, upholstery, etc. Acrylic monomers can be made by reaction of hydrogen cyanide and acetylene and hydrogen cyanide to form acrylonitrile. Figure shows the structure of acrylic and modacrylic. X is cyanide based portion and Y is vinyl based portion. If when cyanide based portion is more than 85 and vinyl based is less than 15%, it is acrylic, whereas when this cyanide portion is less than 85 and vinyl portion is greater than 15%, it is modacrylic. Properties: moderate strength, moderate stiffness and elongation and weight. Excellent resiliency and recovery from bending deformation. Moisture regain is low but higher than polyester. Good chemical resistance to mineral acid and common solvents. Attacked by concentrated acids, slowly hydrolyzed by weak alkalis, unaffected by oxidizing, reducing agents, biological agents and sunlight. Polyalkene fibers. Polypropylene PP, a versatile polymer used both as a plastic and fiber. It is a translucent thermoplastic polymer and possesses good chemical and heat resistance. It is a linear hydrocarbon polymer and its imperial formula expressed as CnH2n. Propylene gas is a byproduct of oil and natural gas production. The degrees of crystallinity of PP is generally between 50 to 65%. Polypropylene is commonly used in consumer products such as furniture, luggage, toys, battery cases and other durable items for the home, garden or leisure use. It is also widely used in packaging and also reusable containers and textile. Polypropylene is also used for filters, face masks and performance textile. It is strong, soft, lightweight and easy to clean. Non-woven polypropylene fabric are some of the most versatile material available today. Many types of high quality performance fabric are made from polypropylene through different processes. It is very cheap to produce compared to natural fiber but is not environment friendly. Polyurethane fiber. Polyurethane, special class of segmented block copolymer of alternating sequence of soft and hard segment. The soft segment is polyether or polyester polyols with Tg well below room temperature. The hard segment, often crystalline, composed of a diisocyanate and chain extender. The hard and soft segments act synergistically to produce a wide range of properties such as elasticity, hardness, tensile and flex strength, resiliency or durability, etc. The soft segment provide elasticity, toughness and resiliency, while the hard segment contributes strength, hardness and elevated temperature performance. While many combinations of diisocyanate, diols and diamines have been explored in hard block segments, methylene diisocyanate (MDI) is the most used diisocyanate, while 1,4-butanediol (BDO) remains as the most common chain extender. Diamines are primarily used with lower reactive toluene diisocyanate (TDI) based polyurethane elastomers. Polyurethane is widely used to make fabric that facilitate freedom of movement and provide great comfort. For example, sportswear, swimwear, medical textile, furniture upholstery, footwear. Biopolymers. Biopolymers are produced by biological systems, for example microorganisms, plants and animals, or any chemically synthesized from biological starting material such as sugar, starch, natural fats or oils, etc. They are more biodegradable than vegetable or animal based natural fibers. Advantage of biopolymers: these are fully bio-based, lesser oil, petroleum oil is required for production, lesser greenhouse gas emission. Disadvantage of biopolymer: competition for biological sources for use as food and fuel, additional sorting material required for recycling to avoid contamination, performance inferior to oil-based polymer, poorer heat and moisture resistance. Application of biopolymer: drug delivery system, medical field; wound closure and healing product, medical field; surgical impact devices, medical field; bioabsorbable scaffolds for tissue engineering; food containers, soil retention, seating, agricultural film, waste bag and packaging materials. Non-amine biopolymers are used in agriculture, filtration, hygiene and protective clothing. Biopolymers of high potential. Polylactic acid. It is only melt processable fiber from annually renewable natural resources. Cornstarch in the United States, tapioca product, that is root, chip or starch, mostly in Asia, or sugarcane in the rest of the world. It is a thermoplastic aliphatic polyester similar to synthetic PET. The sequence of manufacture steps is as follows: corn to starch, then to unrefined dextrose, to fermentation, by fermentation to DLN lactic acid and a monomer production, DL mesolactide, then to polymer PLA production, polymer modification to form fiber, film, plastic or bottle manufacture. Picture shows the structure of lactic acid, lactide and polylactic acid. High strength, good drape, wrinkle and UV light resistant, durable under a range of conditions. Melting point is around 170 degrees centigrade. Density is 1.25 gram per centimeter cube. Reduced flammability. Limiting oxygen index is 25. It is higher than polyester and much higher than polypropylene. Biomedical applications include sutures, stents, dialysis media and drug delivery device. Bacterial polyester biopolymer. Polyhydroalkonates (PHAs) produced by genetically modified microorganisms or modified plants. The resulting polymers are often copolymers from 3 and 4 hydrobutyric acid and or hydrovaleric acid. Using the correct bacteria, PHAs can be produced from wastewater. Poly 3 hydrobutyrate or PHBs can be produced from transgenic plant similar to switchgrass. The bacterial polyester PHAs with poly R3 hydroxybutyrate P3HB, the first homolog, are produced by microorganisms. It is a high molecular weight polyester and thermoplastic that melts at 180 degrees and can be made spun into biocompatible and biodegradable fibers that are suitable for surgical use. Figure shows the structure of PH1B, PHRV and PHB. Advantage of these bacterial polymers, polyesters: production from fully renewable resources, fast and complete biodegradable, excellent strength and stiffness. Disadvantage: high thermal degradability, brittleness and high price. Polyalkylene dicarboxylate polyester (APDs), renewable polybutylene succinate (PBS), produced by condensation of succinic acid and 1,4-butanediol. Its properties are similar to those of PET polyester, common polyester. It is semi-crystalline with a melting point higher than that of PLA, polylactic acid. Tg is approximately minus 32 degrees centigrade and the melting temperature is approximately 115 degrees centigrade. PBS is tougher than PLA in nature, rigidity and Young's modulus are lower. Biosuccinic acid (SA) is produced by fermentation of bioengineered yeast and E. coli. Catalytic hydrogenation of biosuccinic acid produces 1,4-butanediol, which can also be produced by fermentation. Bioethylene glycol is produced from bioethylene, a product of catalytic dehydration of fermentation derived ethanol. Bioadipic acid can be produced by a number of fermentation-based processes. Aliphatic polyesters degrade in contact with living tissues or under outdoor conditions. These are derived from lactides, glycolide and E-caprolactone. They can also be applied in the field of surgery, pharmacy, pharmacology, tissue engineering as well as environmental protection. Common dicarboxylic acid and diol monomers found in APDs are shown in the figure. They include succinic acid (SA), adipic acid (AA), ethylene glycol (EG) and 1,4-butanediol (1,4-BD). Polyamides. Currently, the main attention is paid to biopolyamide composite reinforced by plant fibers and cellulosic nanoparticles, since they offer improvement of mechanical performance without sacrificing the original renewable character of the material. Three main groups of polymers are diamides and diacids, where both monomers or only diacid come from renewable feedstock. Second group of monomer is aminocarboxylic acid. Third group, lactams transform into polyamide via ring opening polymerization. The main raw material is castor oil, which is a mixture of saturated and unsaturated fatty acid, and the main component is C18 ricinoleic acid. Flow sheet of production of various biopolyamides are shown in next slide. Modern biopolyamide based material synthesis and modification. There are two groups of sources. First is biomass, sugar, starch and lignocellulose. Those are pre-treated after extraction and then converted to sugar, fermentation and converted to adipic acid. And these sugar again oxidized to gluconic acid, then converted to adipic acid and 1,4-hexadiamine to form PA66. It can be used for PA46, and another group is making oil from oil crops. Oil crop is pressed to extract castor oil. It is chemically converted and finally prepared PA610 and PA1010 and PA11. These are various biopolyamides. These again biopolymers obtained by shown in this figure are PA66, PA46, PA410 PA610, PA1010 and PA11. Polythene. Polythene is an important engineering polymer traditionally produced from fossil resources. Bio-based polyethylene has exactly the same chemical, physical and mechanical properties as petrochemical polyethylene. The sequence for biological method is as follows: fermentation of sugarcane, sugar beet, starch crop to produce bioethanol. It is distilled at high temperature over a solid catalyst and ethylene is formed, and from that we get microbial polyethylene or green polyethylene. Polypropylene is at least partially made from renewable resources using methanol and metathesis chemistry. Biodegradable polyurethane, PURs. Biodegradable polyurethane are tough, durable, biocompatible and biostable. Unlike polyester derivatives, polyether-based PURs are quite resistant to degradation by microorganisms. Biodegradable PURs are synthesized using a diisocyanate, a diol and a chain extension agent. The reaction between a cyclic carbonate and an amine rendering the urethane bond, avoiding diisocyanate. In particular, polyaddition reaction between L-lysine and a bifunctional 5-member cyclic carbonate in the presence of a strong base. Textile materials were originally made from natural fiber, namely cotton, wool, silk, etc. With the advancement of science as well as with diverse use of textile material, natural fibers are being substituted by synthetic polymeric fiber, mostly polyester, polyamide and polyacrylic. Polyester, being the most acceptable one, has been modified in several ways to increase its water uptake and dye accessibility. Polyamides are used for bright soft products as well as for high abrading materials. Polypropylene is used for its hydrophobic properties and polyurethane for its high elasticity. Synthetic fiber produced from petroleum oils are non-renewable and are not eco-friendly. Hence, biodegradable biopolyester, biopolyamide, polypolyethylene, biopolyurethane are gaining popularity day by day. At present, their production is low and mostly being used for medical purposes. Books authored by me. I have written several books and many, in addition to many edited books, that is multiple authored. Sole authored books are listed below. Number 1, Modern Concept of Color and Appearance, published in 2000, jointly by Science Publisher, USA and Oxford IBH, India. Bostu Shilpe Ranjan and Kostudi Pokriya in Bengali, published in 2005 by Bani Library, Calcutta. Textile Preparation and Dyeing, published in 2006, jointly by Science Publisher, USA and Oxford IBH. The second edition was published by the Society of Dyers and Colorist Education Society, India in 2010. Fourth book, Green Chemistry and the Textile Industry. It is in the form of Textile Progress, Volume 45, Issue 1, 2013, published by Textile Institute in UK. Principle of Color and Appearance Measurement, Volume 1, Object Appearance, Color Perception and Instrumental Measurement, published by Woodhead under Textile Institute book series. Principle of Color Measurement and Appearance, Volume 2, Visual Measurement of Color, Color Comparison and Measurement, released on 13th October 2014, published by Elsevier, Woodhead and under Textile Institute book series. Number 7, History of Textile Coloration, Lambert Academic Publishing, published in February 2, 2015. Principle of Textile Finishing, Elsevier, first edition, published in April 1, 2017. Flame Retardant for Textile Material, published by CRC Press, USA and Textile Institute on 4th August 2020. Number 10, Principle of Textile Printing, published by CRC Press USA and Textile Institute on August 22, 2022.